God made the color purple. God was just showing off. Alice Walker wrote in The Color Purple. And Zora Neale Hurston wrote in Dust Tracks on a Road, research is a formalized curiosity. It's poking and prying with a purpose. And then finally, when I think about the near future, you know, we have this attitude, well, whatever happens, happens, right? So that goes along with the Cheshire Cat saying, if you don't care much where you want to get to, it doesn't much matter which way you go. But I think it does matter which way we go and what road we take. Because when I think about design in the near future, what I think are the most important issues, what's really crucial and vital, is that we need to revitalize the arts and sciences right now in 2002.
Okay, anyway, she's an amazing woman. She went to, I can't remember, I think she went to Stanford, Cornell, undergrad, and Cornell, and she majored in chemical engineering, and then went on to get her MD, and then she was a shuttle astronaut, actually. And then she was a missionary, and now she goes around speaking and trying to influence young ladies into getting into the arts and science, and actually trying to do that fusion of art and science, which I think is admirable and what is needed, because, well, I don't know if it would fly too much in my department, but anyway, all right. So anyway, she's speaking tonight at Pearson at 7. If you want to go, it's... What's that?
Like, were you just randomly looking at that?
Yeah, like last week.
Really?
Yeah, because it's kind of falls into my research purview, since I'm the educator downstairs, not the physicist. All right, but anyway, let's go ahead and let's do this. Let's go ahead and take our quiz. This is quiz 7. All right. It'll be painless. Trust me, I'm going to do this a little bit differently in that we'll go through the quiz and then we will where is it? Quiz 7, here it is. Oh, good. All right. Now, what we'll do is we'll go through this thing, and then I'll give you the answers after it's done instead of as it's going on. So let's go ahead and go to slideshow, view show. Here we go. Here's our first question. This is actually quiz 7. I'll get it straight one of these days, but I do have it down as quiz 7 in the thing. All right, quiz 7, question 1. It says this: when the ball at the end of the string swings to its lowest point, okay, dink, and then the razor cuts it instantly, but it's cut by a sharp razor, which path will the ball then follow? Is it A, B, or C? A, B, or C? I got this one right. I love this guy's conceptual physics problems because you show them around downstairs and invariably they'll miss them. It's great. And they'll go, oh yeah, oh yeah, oh yeah. Okay, so there's the first one. And y'all can talk among yourselves. Figure it out if you want to. Are we ready to move on? You got our answer? Okay, yeah, because we're going to go back and go over the answer here. All right. Okay. Question 2. Which encounters a greater force of air resistance? A falling elephant or a falling feather? Which one incurs more air resistance? A falling elephant or feather? All right. Next question. Question 3. If a Mack truck, which is very massive compared to the Volkswagen, have a head-on collision, hopefully nobody gets hurt, all right, which vehicle will experience the greater impact force? The Mack truck, the Volkswagen, both the same? It depends on other factors. Remember, when you're doing your MCAT or DAT, I finally figured out that that's the one for dental school. Any future vets out there? No future vets? Okay. I don't know what the veterinary test. Never pick this answer. Even if you think it's right, it's absolutely, never pick it. Never pick none of the above, because that's never the right answer, ever. All right. So it's A, B, or C. This last one. Now, I was 3 of 3 so far. Then I got to this question, and I was 3 of 4. Okay, in both cases, an applied force of 100 newtons accelerates this 100 Newton block. All right. In which case is the acceleration greater, or is it the same? In which case would the acceleration be greater, or, so you got case A, case B, or C, they're the same. And you got to think about net force, force equals mass times acceleration for the whole system. That's where I screwed it up. All right, enough of that. Okay, so you've made your choices. Y'all didn't chat too much among each other, but that's okay. Let's look at the answers, and I've got the answers set up in a fancy way, except for this last one. We're going to start with the last one because I forgot, I couldn't find the slideshow for this one. This says it's on, so we'll go to the dot cam, see if that works. I want to go to the dot cam. It says dot cam up there, but it didn't go to the dot cam there. Maybe I got to turn on something down here. Dot cam. There. Okay. All right. Let's turn on this. Oops. Okay. Yes. All right. Cool. All right. Oh, but on that first question, it was actually the one that's being pulled by the hand has greater acceleration because you only have 100 Newton mass moving. Okay. Well, that you only have one mass that's getting pulled with a force of 100 newtons. On the other one, you had the whole system is moving, and so it's going to accelerate a little bit slower. All right? See what I'm saying? Yeah, it's one of those tricky ones.
But the Newton is actually, yeah.
Right. So that whole system had 200, had well, whatever 100 divided by 9.8 is, let's say around 11, or one was 11 kilograms. You had 2 11 kilogram things. Well, that's 22 kilograms getting accelerated with a force of 100 newtons. And the other one was just the 11 kilogram force, or 11 kilogram mass getting pulled with 100 newtons. See the difference? So the F equals ma was very different. All right, let's go back to the one question we had here. The first one about the ball on a string. There you go. We're going to do the ball on the string thing. Can you all see that? There it is. There was the question. Which one is it? A, B, or C? B? Really? A. Nobody fell for C? Okay, good. Because the answer is B. The answer is B. Once we cut the string, because it's horizontal velocity right here, right? And so it's just going to keep going, but then gravity's going to take it over, and it'll do. So it's just like the little problem on the test where we threw, at that point, where we threw the ball off the bridge vertically. That's that one. Okay, good. All right, elephant falling. Which has the greater force? Which has more air resistance? The feather or the elephant? The feather? Which is plowing through more air, the feather or the elephant? The elephant. It's going to experience a lot more air resistance. However, he's so massive that it's not going to affect him hardly at all. Okay? It's not going to affect him hardly at all. I think is what they say. I've only read this like 8 times. Yeah. there's a greater force of air resistance on the falling elephant, which plows through, I like that, that's a scientific term, plows through more air than the feather in getting to the ground. The elephant encounters several newtons of air resistance, which compared to its huge weight has practically no effect. Only a small fraction of Newton acts on the feather, but the effect is significant. Remember, they say, this is what I like down here, remember to distinguish between a force itself and the effect that it provides. Okay? So the little F equals ma on the elephant is not enough to affect like it affects the feather. All right, last but not least, here we go. Mack truck. A, B, or C? C. Exactly. Exactly. Which one's going to have, but what about the accelerations? Which one's going to have the greater acceleration? The Volkswagen or the truck? And when they hit, it's bigger. So what's going to be its acceleration?
Wouldn't it be just plowing through the small car with greater?
Actually, they're going to stick together, and they'll have the same acceleration, right? No. But actually, this Volkswagen will have greater acceleration because it's going to feel the force, and it's got less mass. F equals ma. The force on the truck, this guy's going to have greater acceleration going this way. The truck will have less acceleration going that way, and it'll probably bounce off.
Is that just like saying if you pick a point on the car, like in the middle, like the center of the Volkswagen, took it from where it went to the impact?
Yeah.
So it would go farther.
Oh, no, not that, not that. No, oh, that's very complicated. No, we're not, ooh. That's something automotive engineers would figure out. Unemployed no. Anyway, so the force of the truck divided by the mass of the truck on the car, small acceleration. The force on the car divided by the car, big acceleration, because these two guys are equal. Equal and opposite, Newton's third law. Okay. All right, so that was fun. There we go. Now, don't forget, I'm going to have to collect that here in a minute. All right, now, I think everybody's back. Okay, that's that. We'll escape out of that. All right. Just a minute. There's one other thing I wanted to... Have you all seen my Dancing with the Stars 2030 picture? No? Okay. This is commercial break real quick. Dancing with the Stars 2020, maybe. Oh boy. All right. Okay, not in a million years. All right, now I had one last thing to waste your time with. Oh, here it is. Here it is. Now, I've been to airborne school, and I've done some dangerous things, but I still have a fear of heights. This has nothing to do with physics or anything, so those of you watching at home, just relax. It's time to go get a milkshake or something, or go get a beer. Now I lost the damn thing. Where was it? Here it is. Here it is. This is some site in Norway. It's kind of a tourist thing, but it's really wild, and it shows some neat forces later on in the thing, so I guess I can tie it in that way. But take a look at this thing. All right, this is translated from the Italian, but this is someplace out in, oh, gosh, you're annoying. All right, now, so here we go. There's this place out in Norway, and there's this mysterious rock that rises 600 meters above this fjord, and it's breathtaking. It is breathtaking, but where do you see what these tourists do when they go here? It's amazing. Whoa, that's a little noisy. Okay, there's the trail that we're going to take to get up there. So we've got about a 2,500 meter climb to get up there, change in elevation here. All right, so here we go. They're beginning the climb. I can do this. I can do that. That one looks nice. Trail goes on. Now it starts to get a little bit tricky. My wife and I went on our honeymoon 10 years ago to Maine, and we thought we were going to go on this nature trail, and it was like this. And I'm like, oh my, this isn't what we signed up for. Anyway, okay, gets a little bit, climbs a little bit more. Now, here's where I started to get a little bit nervous. When you've got to kind of inch along like this, along a cliff, I don't like that at all. I don't do that anymore. So right now is when I'd start to go, oh, okay, but bring the kids. It's starting to get a little bit steeper, a little more dangerous. And now we're almost to the top. Now here's, I mean, just right away, I'm just going, okay, I'm done. But, I mean, every time I show this to students, my palms start getting sweaty. But anyway, and here we are finally. All right, now, okay, there's no fences. There's no nothing. I don't know how many Norwegians are laying in the bottom of this fjord, but they're just out there. Playing a little Enya. Here, relax. I'll turn it down a little bit. Yeah, the rest are just pictures of when you're up there. It is beautiful. I mean, it's something to see. But, yeah, Grandpa not affected? I think so. Grandpa's like, oh my. That's the way I'd have to low crawl out there if I even got that far. But some of these people, oh my. See that guy? Ah. Oh, look. He's sitting. Oh my. Oh, this is not when you say, I think we should start seeing other people. That would be bad. Then they got this big rock. Whoa. Oh my. No, no, no. Oh dear. Then there's this big fissure that split it, and then there's a big rock. Oh. These guys are crazy. Well, that's actually one guy falling. Ah, hey, nice parabolic motion, you know. His vertical velocity, now he's going to go down, but he's going to, yeah. There's a bunch of them going. Now here's the look at that. Big rock. And then, why? I don't get that. There's some more pictures of it. Of course, there's always somebody who's got to... Okay, anyway, there's 5 minutes of your life you won't get back. All right, those of you that were watching at home, hope you enjoyed your beer. All right, now, basically, I was, like I said, I didn't know about Maya Jameson. I can't stay. I've got other plans. But if y'all want to go, it starts at 7. But we're going to talk a little bit more. What I wanted to do was actually turn this off and turn off the projector and do some homework problems. Make it worth your while to come in, because we got way ahead of the other class, and I kind of realized that maybe we weren't ready to start energy yet. I wasn't ready to start energy yet. But you all been to your lab, right? Last night? And what'd you do? Circular motion, right? We haven't done that in class. So let me explain what was going on there, all right? Real quick. So we'll do a little circular motion, then we'll do some homework problems. You'll be out of here by about 6:15, 6:20, right around there. All right, now, I am good at freehand circles. I impressed myself. Never know I taught geometry, little gangbangers for 10 years, and you had to draw them like this. All right. Okay, so there we go. So we got a circle with R. Now, uniform circular motion. UCM. Uniform circular motion. Uniform means the speed is constant. Notice I didn't say velocity. The velocity is not constant. The velocity is always changing because it's always changing direction. Because it's always changing direction, guess what? That means there's an acceleration. Okay? And so that creates a net force towards the center. All right? So when you're driving in the car, like I used to have this big old, well, my sister had it back in the, it was her car that she went to college on back in the late 70s. It was a 1967 Mercury Monterey that she owned. Okay, this thing was huge. I mean, like I said, it sucked up Toyotas in its wheel wells as it went down the highway. But anyway, if you went around a turn, because it had like these leather seats, and the thing was like 9 feet wide. And if someone was sitting close to you, like you had your date or something like that, go around fast, whoosh, bam. She goes off on the other end because she wants to keep going straight, but the car's turning, all right? And so there's nothing, and since there wasn't strong enough friction in the car is actually accelerating when it comes here, accelerating towards the center. It's got an acceleration towards the center everywhere. Even though the velocity is tangential, the velocity is tangent to the curve, you got an acceleration, it's always towards the center. Okay? And since it's uniform circular motion, you got a constant speed, so you can figure out the velocity. And the velocity is pretty, or you can figure out the speed if you know this. If you know R, what's the distance that you would go around here? How would you find that distance? What is that? Huh? Circumference of the circle, which is 2 pi r. Right. Okay, so you got 2 pi r, and then the amount of time that it took you to get around there is a capital T. We call that a capital T because we call that the period. Okay, and I think this is all language that might have been in your lab, right? And you guys are going, what are they talking about? The period is how long it goes around. Did they talk about frequency? Frequency, they did? Okay, frequency is easy. Frequency is just 1 over the period. You just take the period and flip it over. Okay? All right, so, and that's how many trips it'll make in a certain time. In other words, if something like our frequency of our AC current that we have here in the United States is set at 60 hertz, so that means the generator goes back and forth, boom, 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 like that 60 times in 1 second. Okay, this period is not quite that big, but anyway, so you got 2 pi r. So this would be your velocity or speed, actually. Let's call it a speed because the velocity is always changing. Okay, and that acceleration. Okay, since this thing has a mass. This thing has a mass out here. The net force, the sum of the net force, and I'm going to put it R because it's going radially inward at all junctures. So you got this FR2 is equal to MA, which is equal to mv squared over R. We could go through the long derivation of how we get v squared over r as the acceleration, but we're not going to do that. I'm just telling you. Acceleration, A, is equal to v squared over r for uniform circular motion. That's your acceleration. So that's the net force that's being applied. So you've got this screwy question, which I really like, on your lab, okay, that says, what's the normal force of someone standing on the equator? Their weight. Well, normally, we'd think of the normal force if we got a person, okay, if we got a person standing on a scale, they've got mg, and they got a normal force going straight up, which is n. And if they're not crashing through the center of the earth, and if they're not flying up in the air, then the sum of the forces is equal to what? 0. So the normal force equals mg. However, on the equator. Let's just draw the Earth here. Here's the equator. And the Earth is spinning around this way. And let's put our person here on the equator. Let's say I'm standing there. Or Barack Obama. One or the other. All right. Either one. Spinning around. Now let's look at our normal forces. Okay? Now, we've got a force going in. It's spinning, though. We've got mg going in. And that mg is caused by this huge mass of Earth and my little mass here, or Barack's little mass here. That's causing the mg attraction. He's pushing on the, he's standing there in Brazil, checking out, telling the Brazilians not to cut down their rainforest anymore. Okay? Save the planet, and they're saying we need to eat, so we got a problem. But anyway, that's different. That's poli-sci class, not physics. All right, so we got a normal force going in, but since he's spinning around, he's also got, there's a net force. If I'm going to draw the free body diagram, actually, I've got N going this way, mg going this way. But remember how we always have that acceleration on our free body diagram? I've got an acceleration actually going this way. Okay? That's my net force. And that net force is caused by the spinning around, and that's our mv squared over r. So, when I look at the sum of the forces in the r direction, or just in the x direction, if I drew them over here, it'd still be the same. It'd still be going in, normal force going out, with an acceleration going like this. Still work out the same, but since we're going this way, we've got a negative mv squared, so we've got negative ma equals n minus mg. Yeah. And we talked about that this minus ma is actually minus mv squared over r equals n minus mg. So the normal force is actually equal to mg plus or minus mv squared over r. I just did a little algebra there. So that's the answer to that one question on your lab, is why is it different? Why is the normal force less on the equator? And what is the normal force on the equator? Because if he's standing on the North Pole, same guy, goes up to the North Pole, he doesn't have that spin anymore. All he feels now is mg and the normal force. Those are the only two forces. There's no spin anymore. So you're actually lighter on the equator. A little bit. Yes?
Nothing to do with the distance from the center.
It has everything to do with the distance from the center. Because, as James is getting to, if we're up here on this parallel, what parallel are we on? 54? Something like that? 30, we're on 38? 38 north? Okay. So if we're at 38 degrees north, we're going to be, the r, this is what James is kind of getting at, the r is a little bit less. This r prime is a lot less than this r here. And so my mv squared over r will be less. And it keeps getting less and less and less and less until it goes to 0. Okay. So it isn't 1, and then it becomes infinite, actually, when you start dividing that way. Then it becomes something else. Okay. Ooh, that's an interesting thing.
If you're at 30 degrees, wouldn't the radius still be the same?
What's that?
If you're on the 38 degree, wouldn't it still be the same? So the r would be horizontal to the center. It'd be like some of the vertical and a horizontal.
Oh, no. It'd still be the same r. Still be that's a tricky problem to try and figure that out. Yeah, because this would be 38 degrees. You'd have to figure out what this is and then be able to right. That's a tricky little problem. But the r, but actually, see what happens is my r gets smaller, and since r gets smaller, what happens to v? It gets smaller. And so eventually, because here's how I find V, right? So as R goes to 0, what happens to my V? It goes to 0. That's why when you're up here, it's 0. Okay? All right. I knew I'd get myself out of that bind eventually. All right. Well, anyway, so that's that. That's uniform circular motion. Our book doesn't pick that up till chapter 7. I forgot about that. When I changed books, the lab, everything else should be fine, but the lab kind of got out of whack with the book. All right, now let's talk a little bit about, let's do some homework problems. Yes?
So as you get farther away from your center, isn't it like inverse, like the longer your R gets, your radius gets, the less the effects of gravity have on the outline of the body?
Yeah, but your velocity goes down.
Velocity.
Right, and so your velocity goes down, so you don't feel as much spinning around. So up here you have none. There's none. Right. Yeah. Okay. Now then, let's take a look at your homework problems. I think the first one, the assignment 6, is actually pretty easy because it's all multiple choice except for like 2 of them, and you get infinite guesses. So that's pretty easy. All right. And hopefully you learn something from it. Okay. But let's talk a little bit about the friction problem. Or actually, I think I gave you an ice skater problem that I really liked. The sprinter during rescue. Oh, Olympic ice skaters. This is problem 32. So let's start with this one, because this is Newton's third law. For every action, there's an equal and opposite reaction. All right? Well, here's the problem. Let's at least get it set up here. The problem is this. In an Olympic ice skating event, a 65-kilogram male skater pushes a 45-kilogram female skater. Okay? Now, when they push each other, while they're in contact, he pushes, let's say he pushes her with a certain force. What does she push back? Let's say a force of 1,000 newtons. I don't know what it's going to be, but say he pushes her with a force of 1,000 newtons. How much force is she pushing back with? 1,000 newtons. But since her mass is less, so her free body diagram looks like this. Female skater, the mass of the female skater is 45 kilograms. He's pushing her like this with this force. Okay? And so she's got the sum of her forces in the x direction. Oh, well, that's an acceleration. Remember, with your free body diagram, you draw all the forces that are in there. In this one, we don't really need to worry about mg and the normal force, but we'll go ahead and put them in there just so we get in the habit. And so the sum of the forces in the y direction equals 0, because she's not accelerating. He didn't like push her up or anything like that, or throw her. I forgot. I'll do it when we get to momentum. I've got the Chris Farley thing where he's skating. Do y'all remember that one? Where he's doing the Olympics? It's hilarious. But anyway, so, Fy, so this would be n minus mg. That doesn't help me much. But the sum of the forces in the x direction, oh, we actually have an acceleration going this way. So that would be 45 times a equals that force that he pushed her. Okay? Equals that force that he pushed her. Okay? Now, his free body diagram looks like this. He's going this way. Same force. This guy and this guy are equal to each other. He's got a normal that's a little bit bigger. Normal of the male. Mass of the male times g. And so he's got forces in the y direction. Again, just get in the habit. I always get in the habit of doing that. Equals n minus mmg, because you need those when you start doing the frictional force. And he's actually accelerating in minus m some a of the male skater. This, we'll put a of the female skater here. Equals the negative force. Now, they said here, oh, he caused her to accelerate at 2 meters per second. So if the acceleration of the female skater is 2 meters per second squared, we know the force now. 45 times 2 is 90 newtons. So the force in the positive direction is equal to 90 newtons. So this one becomes equals negative 90. And this would be minus 65 a of the male. So we can get his acceleration. And when we divide it out, it becomes a positive number, but we know that it's going this way. So we take care of it there. Okay? Thought I'd role model how to do a few of these problems for you. Okay. Now, so that was a pretty, that one wasn't bad. All right. Now let's talk about friction. We'll do 2 of them. We'll look at problem 64 and we'll look at problem 68, but I won't solve them completely. Okay? So 64, problem 64 says this. A physics professor is trying to move he's got a desk that weighs 35 kilograms. And when he pushes on it, he's got to push all the way up to 250 newtons to get this thing to move. Okay? He's got to push on it with 250 newtons. So here's the desk. Mass of the desk is equal to 35 kilograms. And this is on the friction part. And so he pushes he pushes with 295 newtons, or 250, what did I say? 275 newtons. He's pushing with a force of 275 newtons. That's right when it gets to move. Okay? So what's pushing back on the desk? Friction. Friction's pushing back. All right? Friction's going, oh! That's the other force and it's going to be the static friction. And it's going to be the maximum static friction. All right? Now, when we deal with friction, that means, because here's the formula for static friction, and the formula for kinetic friction, which we'll use later, is mu s, that's the coefficient of static friction, times the normal force. Okay? Now don't get, when you're looking back at your notes, don't get the newtons mixed up with normal force, okay? That'll be easy to do. All right? So, we need a normal force. Where do we find the normal force? That's in the y component. So that's why I always get in the habit of doing the y component every time, because eventually you're going to have to use it when you're starting to use frictional force. So you got mg, newtons, or not even newtons, normal. There we go. I knew I'd get it eventually. Oh, this is equal to the coefficient of kinetic friction times normal. Now, this problem is asking you, they want you to find this, and then later on, when he actually starts to move the desk, what happens to this force? It drops down. Because remember, it goes static, 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 push hard, and then this is static, and then you get to Fs max. It finally gave. And then that stays pretty constant. All right. Good. Okay. This, and I like this problem because because it deals with a couple of other issues once we actually start to move it. All right, so right now, the sum of the forces in the y direction equals 0. It's not flying, so this equals n minus mg. So the normal force is equal to mg. Okay, and it's not accelerating, so the sum of the forces in the x direction, it's just getting ready to move. It's not accelerating yet, so it's at 0 also. In other words, we don't have this a here is equal to 0. Okay? All right. So let's take a look at our forces. We got 275 newtons minus the force of static friction, the maximum force of static friction. Oh, wow. Looky, looky. The force of static friction equals 275 newtons. We also have a formula for the force of static friction, so we can find this. So we go, oh, okay. So the force of static friction then equals mu of s times the normal force, which was mg, equals 275. I think we can figure out what the coefficient of friction is. Now, the next question that they ask in that problem, is this. They say, he gets it moving, 195 newtons, okay? Then once he gets it to move, it's going 195 newtons at a constant velocity. So what's the acceleration? So 0. 0. If it's going at a constant velocity, then your acceleration is 0. All right? So it turns out to be the same problem. But this time they want you to find the mu of kinetic friction. And it's the exact same thing. You just got to remember on problem 64 that when it says constant velocity, I'll just give you this hint, constant velocity, and then you all can work it out on your own. Constant velocity means A equals 0. So the sum of the forces in the x direction then would be 0 equals 195 minus the kinetic frictional force. Okay. There's a nice little problem. All right. Now let's look at problem 68 real quick. We've got, this is a little bit like the Superman problem. Remember, you've got to, don't forget about the things you learned in chapter 2. All right. This one is a hockey player whacks a puck at 5 meters per second. Okay. Launches it off. It leaves a stick. So once it leaves a stick, there's no more forces acting on it, except for the force of kinetic friction of the ice, which will be slowing it down. So we've got this hockey puck. He's got an initial velocity of 5 meters per second. This way. He's going this way at 5 meters per second. Which way is, if he comes to a stop, which way is his acceleration going? Right, to the, correct, to the left, right? Correct, yes. So we've got the acceleration going this way. So A is going this way. That's the only force that's working on it. This is kinetic frictional force. So we go, oh, okay, well, this looks pretty easy. Then the sum of the forces in the x direction, well, we got the sum of the forces in the y direction equals 0, which equals n minus mg. Remember, we're dealing with friction, so we always got to go to the y-axis. And so we've got n equals mg. I'm going to slide this down a little bit further. And we know that the coefficient of friction then, or the kinetic frictional force, is equal to mu k times mg. If it's on an incline, it's mu k times mg cosine of the angle of the incline every time. Okay? All right. Now, Okay, so this thing seems pretty easy so far. We go, all right, well, f of x then equals, it's got an acceleration that's going this way, a negative ma, equals, oh, negative mu k times mg. They want us to find out what mu k is. First of all, they had the audacity not to tell me what the mass of the puck was. That was the first thing. Secondly, it comes to a stop, so its V final is 0. And luckily, they did tell me it came to a stop within 20 meters. So it traveled 20 meters and came to a stop. And they want me to find this guy. Well, first of all, do I need the mass of the puck? Do I need it? No, it looks like it cancels. Looks like it cancels here. Right here we got, in fact, let's just cancel the negatives too. So we wind up with A equals mu k times g. Okay, so mu k equals A over g. Well, that's great. Fine. Super. What am I supposed to do with that? Well, we got to find A using our old Chapter 2 problems. Our Chapter 2 equations of kinematics. In other words, you got an initial velocity, you got a final velocity, and you got a distance. Can you find the acceleration that it went through to slow down? Because you got this guy. Okay? Which will give you, you went from 20, or 0 to 20, so 20 minus, yeah. It's a negative acceleration. Okay? So you should be able, you get 25 over 40. Its acceleration is not much, but it's there. And the mu k is not much for the ice. Okay? 76 is a great test type question because it covers everything. If you want to read ahead. I don't think I signed that one, did I? I don't think so. But that's all I've got. I even tried to stretch it by showing you that little slideshow. Okay? But we're done with Chapter 4.